All right, well, so I want to start this afternoon with a little bit of a survey. So I want you to raise your hand if you have ever heard anyone come to you and say any of these phrases. Stop asking why 5 times. Don't bother holding a retro after 72 hours. Postmortems are not for remediation items. Oh, we're blameless. Nobody here does anything wrong. Oh, chaos engineering. Let's blow up production for fun. Or root cause does not exist. So if you've ever heard any of those, raise your hands. All right, keep your hands up. Keep your hands up if your reaction to this in the back of your mind was something like this. Yeah. So when a lot of these phrases and a lot of these ideas come from sort of the safety sciences and resilience engineering crowd, which is a group of people that have been looking at what safety means in a lot of different industries for quite a while, about 70 years. And then at some point, like, we figured out computers might have a component of importance in our life. So it's like, well, how can we be safe when we operate computers? So there's a bunch of us, actually, that are in this space looking at this stuff. And by the way, I stole this slide from John Allspaw, so I am not actually John Allspaw. But he had a great slide of everybody who's doing this work. So as I was thinking about what to talk about and how to approach this particular topic, I sort of realized that it might be more useful to give you all some context. So I'm actually, conference organizers love this. I'm not actually going to do this talk. I'm actually going to do this talk. Now, if you were here to hear about how automation is going to kill us all, don't worry. We will see Sharky later in the talk. I am actually going to talk about automation, so we won't lose that. But I do want to provide you all with a little more context and a little more understanding about why we're saying those weird things like MTTR is not a thing we should pay attention to, or human error doesn't exist. And we're going to use the lens through which we look at these things. We're going to look at them in 3 acts. We're going to look at them through the lens of incidents. I was actually having lunch here today, and I was asking someone that I was having lunch with, have you found in your work that you're dealing with more incidents? And he nodded his head and said, yeah, it seems like we've, over the years, been having more and more. And so that might resonate with you, and again, we're going to look at it through incidents. So this is the obligatory About Me slide. I'm not going to go through it except for 2 things. Paul Reed on Twitter. If you want to tweet me, that's totally cool. And then also I do... when I'm in the office, applied resilience engineering at Netflix. So I spend my days thinking about resilience in large socio-technical systems, and that's what we're going to talk about today. So I want to do a little thought experiment with you. I want to start with a thought experiment. I originally did a talk a number of years ago now that posited, well, what if we think of developers as pilots and operations systems administrators as air traffic controllers? What could we learn from aviation if we thought about the world that way? So there's a link if you want to see that talk, but for the thought experiment, we're going to go to an incident in the JFK data center. This is a real conversation between an air traffic controller and a pilot. Now, I want to say something. I am going to ask you questions about this later, so pay attention to what's going on, because I promise you we're going to talk about it later. I'm going to ask you questions. All right.
American 2 Heavy, ILS 22 left approach.
American 2 Heavy, Kennedy Tower, runway 22 left, you're number 2 for the field. Traffic's on a 4-mile final with 31 right. Wind is 320 at 22, clear to land, runway 22 left.
And 22 left, American 2 Heavy. Heavy visual for 22 left.
American 2 Heavy, 22 left, you're clear to land.
Clear to land, 22 left. Your localizer's not orange.
Okay, I will double check it. American 2 Heavy, I just reset it. Should be coming back up in a little while. Wind now 320, 3 gusting to 3.5.
Get 22. We can't land on 22. We're breaking off approach, and if you don't give us to runway 31 right, we're going to declare emergency.
All right, I'll pass it along. Fly runway heading for now.
Okay, we're declaring emergency. We're going out 31 right. We're going to the left, and then we're coming around.
American 2 Heavy, just fly runway heading.
The area.
Okay, you're saying you're declaring emergency at this?
3 times I've told you that. 3 times we're declaring an emergency.
Okay, I just want to verify. I know you told me if you didn't get 31 right, you would have to declare emergency. Okay, I understand. Fly runway heading, and I got to get you a turn.
No, we can't.
JetBlue 62, the left on Alpha and monitor ground to the ramp.
That's Alpha, I'm on the ground. JetBlue 62.
I head in 180.
You know, American 2 Heavy, we are turning around to the left here and landing on 3-1. Remove everybody from our way. We've declared an emergency.
All right. Sounds a little stressful, especially, I'm sorry for flying into JFK, sorry, tonight. But I have a question. Was this event a success or a failure? And then somebody asked, did the plane crash? So I want you to think about that. I want you to simmer on that question. We're going to come back to this example. But let's get on to Act 1. So resilience and resilience engineering in incident response. So one of the questions I want to ask you, if you've ever thought about or asked your colleagues, how do you know what to do when an incident is occurring? Have you ever thought about that? How do our teams know what to do when we're in the midst of an incident? Well, this is a question. I'm still on all sorts of slides from John. This is John Allspaw. This is a question that Allspaw asked in his thesis in the Human Factors and System Safety program. Trade-offs under pressure, heuristics and observations of teams resolving internet outages is the very fancy academic name. And in it, he studied an outage at Etsy. And he looked at all of the ways that engineers at Etsy thought about the problem and tried to answer that question. How do we know what to do during an incident? So we're going to go through 3 of those heuristics, and I want to see if any of them resonate with you. If you find that when you're dealing with an incident, there's something that you end up that goes through your mind as you're sort of processing what to do. So first one, change. So what has changed since the last time the system was in a good state? So those are things like, was there a code push? Was there a network change? Was there, other infrastructure, a chef or puppet run or something like that? And so he found that engineers, the first thing they look at is change. Now, in this particular incident, what he found was there were no changes. There were no infrastructure changes. There were no code commits. There was nothing. And yet they still were in the midst of an outage. So something really weird was going on here. When he was able to talk to the team after the incident, what he found, the second heuristic that engineers use is this idea of going wide. So what they do is they think of the entire universe of problems that it could be. And the way that he described it is it's a breadth-first search where we go as wide as possible to see what we can think about. And as soon as we find something, then we switch to a depth mode where we try to figure out if that's the issue or not. But if that doesn't work, we go back to going wide. So it's really, we imagine in a universe of possibilities what could be going wrong. And then the third heuristic that he looked at was this idea of convergent searching. And what's interesting about convergent searching is you might ask yourself, well, as an engineer, how do we know, or how do the engineers know to switch from very wide investigation, what are all the possibilities of things it could be, to, oh, I think it might be this one issue. I think it might be the database, so let's go down that road. And it's this idea of convergent searching. So what engineers do is they use it to both confirm, and this is the important part, and disqualify diagnoses by matching signals and symptoms that they see. So it's not just, hey, it looks like it is the database. They also use it to lob off parts of the tree or parts of the universe where they're like, nope, the database is good, so we're actually going to maybe ignore that in our search space. Now, there was an interesting thing that he found about the heuristics that engineers use to confirm and disqualify these things. And what he found is that engineers use a specific and past diagnosis to make that switch and to look at the universe, or they use a general and recent diagnosis. So what does this mean? Well, it basically means engineers use a really painful incident memory. These are the memories that we carry with us throughout our career, where we say, oh, I've always had problems with Redis or EV Cache or whatever it is. And so I'm going to take that story, and when we have a problem that looks like it's vaguely data store related, and maybe if we have an EV Cache on our stack, I might go look at that, whatever it might be, right? The other thing he found was an incident that is still in your L1 cache. So these are incidents that are very recent to us, and we use them to actually inform the space of the universe that we'll search. So as an example, if we've deployed, maybe we switched from MySQL to Postgres. And so in the last 4 weeks, we've had a lot of weird database problems where we didn't get the conversion quite right. So if we have an outage, we might say, oh, let's check to make sure we're not seeing errors in the Postgres log, because we did see them a lot recently. So these are the sort of two ways that engineers, in the midst of an incident, start to parse like how they go about searching for these things. And one thing I'll mention, he tells a really funny story about two engineers that debugged this particular case that he studied at Etsy. And the solution that turned out to be the correct solution, the reason the one engineer found it is because it happened to be, I think it was EV Cache or something like that. And the point is that the first week that they were on call at Etsy, they had EV Cache problems. And that was so impactful to them. 3-4 years later in their career at Etsy, they always said it's EV Cache. And they turned out to be right when all of the other engineers didn't really think that was the problem. The other really interesting thing is he interviewed an engineer after the incident, and he sat down with him about 2 weeks later and he said, do you remember the incident on this specific date? And the engineer said, yes, I do. It was the outage with da-da-da-da-da-da. And they were completely separate incidents. It turned out that the engineer had encoded a problem that they had been experiencing in the last 6 weeks and ascribed that problem space, I think it was database caching or something, to this incident, and it wasn't involved at all. They weren't related. So you might ask yourself, okay, well, this is kind of academic. Why would we want to know this? Well, it goes to the question of how do you get better at knowing what to do when an incident is occurring? How do we cultivate our teams to get better at doing this particular thing that John described? Well, to discuss that, it helps to talk about what is called the elements of expertise. So what does it mean to say someone's an expert or somebody has expertise in something? So there's a great paper where they talk about this. And they argue that experts use their knowledge base to recognize typicality. So that means they understand when something looks normal. They have that, they can just kind of go up to the big SunSpark server and they can just touch it and see, oh, it's running fine, right? They can make fine discrimination. So as they're in the midst of doing something, they can make fine, subtle changes that people that are less experienced won't even notice. You see this a lot in playing music. Musicians will make fine discriminations that the audience won't pick up on, but they certainly do, and the people they're playing with will as well. They're able to use mental simulation. So this is important because the example they give is in the fire department. The fire department will roll up, and they talked to a bunch of firefighters, and they said they can figure out how the fire got to this point. They can simulate, oh, based on this, I think this is probably what happened. And they can also simulate into the future based on their past experience. And finally, they use their knowledge base of their past to apply what they call higher order rules. And this is basically they know when to break the rules. Those are higher order rules. They know when it's okay to do the thing that you wouldn't tell the junior engineer to ever do. Now, what's interesting about this, it's not that junior engineers don't know how to apply the higher order rules. It's that they don't have the knowledge base to be able to make the informed decision, which I think is really interesting. It's really about the experience, not about the mechanism by which they can apply to figure out when it's okay to break the rules. So I really like this quote: with experience, a person gains the ability to visualize how a situation developed and to imagine how it's going to turn out. And this is the important key point here. Experts see what is not there. There's a great example that they give where a new employee might come to an office, and I've been guilty of this certainly. They'll look at all of the sort of projects, maybe there's 3 or 4 projects in flight, and they'll say, well, like 2 of these are behind schedule, and 1 is having problems with its launch, and 1 went okay. But what they don't recognize is all of the stuff that's happening that they're too new to recognize that's working out perfectly. All of the projects that are humming along that they don't even have a signal that something has gone wrong. That's an example of experts in that system and in the context of that workplace can see what's happening, what isn't there, right? The absence of things. in our work, the question might be, and we'll revisit this, asking the question, why is the site up, as opposed to why it's down? So how do we actually transform experience into expertise? Well, personal experience, the opportunity to continually be challenged, this is important, and I'll contextualize that in a sec. Directed experience, receiving tutoring so as to be able to tutor, and this is really important, and I'll come back to that as well. Manufactured experiences, so training, simulation, things like that. And then, of course, vicarious experiences. This goes back to that painful, memorable events in our careers that we craft into stories. We tell them out in the hallways at conferences. We will always remember them. So what does this actually look like in our industry? Well, on call. If you go on call, you're hopefully going to continually be challenged, and that's a way to add to your personal experience. Direct experiences, that's why you'll see teaching, code review. And here's the point about that. We do code review to review code, of course, but teams that really double down on doing code review well, the reason they do it is because it's learning how to give good feedback to someone. You give code reviews to someone so they know what it looks like to give a good code review to someone else. That's creation of expertise via this type of directed experience. Manufactured experience, so chaos engineering, game days, that's where you're hearing a lot about those things because it helps us create expertise. And then finally, I remember this one incident where it was DNS because it's always DNS, right? I love this quote, success comes from experience and experience comes from failure. So remember that. The second way you can build expertise is exploring discretionary spaces. So this is the Rasmussen triangle. It was done by a safety science researcher who studied 3 Mile Island. And the boundaries here are, on the upper right, you have the boundary of economic failure, on the lower boundary of unacceptable workload, and over here you have the boundary of functioning and acceptable performance and risk. So what does this mean? Well, economic failure means it's too expensive. If it goes over that boundary, we wouldn't pay for it. A customer wouldn't pay for it, the business wouldn't pay for it. So that boundary is how expensive things are. Lower boundary is us at the sharp end of the system, the people doing the work. We're always looking for ways to optimize what we're doing. So we're always going to try to find, optimize things so we can get more work done per unit of time or unit of effort that we have. And then finally, that acceptable risk, that's when things go boom. So in this model, you've got things where the business is pushing cheaper, better, faster, right? They want us to do things cheaper, better, and faster. We're looking for maximum work for the least effort. Where are we both pushing this system? What boundary are we pushing it towards, right? So in the model, he said there's a dotted line, and there's this idea of the discretionary space. Okay, this is all fine, great, triangles, what's Paul talking about? The point that I want to make here is when you talk about organizations like Google and Amazon and Netflix, and it's like they're really good at what they do, it's not that they don't have incidents. It's that they're really good at exploring the breadth of this discretionary space so that when they get close to the edge, they can slow down. They can pull the system back. They can say, wait a minute, we are close to this edge. And the reason we know we're close to this edge is because we explored this space. All right, we're going to come back to this in a sec. So Act 2, resilience in incident analysis. So I'm going to start talking a little bit about who here, by the way, a question because I'm actually curious, who here does retros or postmortems? That's very good. Okay, lots of hands going up. Okay, so these are a couple of anti-patterns that we see in incident analysis when we as resilience engineers, that group of people that we observe when we watch people do retrospectives or postmortems. And one of the big ones is one of the one I mentioned before. We tend to only review failure. We don't ask the question why the site is up. Now, here's an example to help illustrate this a little bit. A lot of times, the reason we're having an incident is because we're pushing systems to their boundaries. So this landing looked a little weird, but they made it down, so that's cool. And then you have this pilot that's like, that's kind of, it was at the end. That's not so good. But they got down, so that's neat. And then you have this pilot who got themselves into quite a bit of trouble. The wing scrapes the runway right there, and then they're not even on a runway anymore. But they went around, and so, okay. And then you have this, California, bright, sunny day. Everything looks lined up, looks great. And that happened. Now, I doubt any of you want to be on any of those planes, but which one got the postmortem? That last one, right? So it turns out that we can learn a lot, and potentially even more, when we study success, when we study what it looks like when we get to the edge of the boundary. All right, one of the other resilience engineering anti-patterns that we see in analysis, retrospective postmortems, forgetting about bias. So somebody asked, well, in our first example, did the plane land? That's outcome bias, right? We treat how we think about an incident differently if we know the end, and we might want to know the end, what happened, right? Hindsight bias, another example, another common one, where things that we've done a million times suddenly look very bad only when there's an incident, right? We only say that that behavior is bad because we know we have the benefit of hindsight. You'll see this a lot as counterfactuals. If anyone has ever asked you in a retro, why did you do that? Why didn't you do that? Why didn't you notice why didn't you notice the printer was out of paper, or the disk was filling up, or whatever? That's a counterfactual. That's hindsight bias. Correspondence bias, this is one of my favorite ones because you see it a lot in development and operations. Basically, it's the idea that we ascribe characteristics to people based on who they are, right? So if you're in operations, you're like, oh, it's developers. Why do they have to deploy every day? Can't they just deploy once a quarter? It was so nice when it was once a quarter. And then, of course, the developers are like, those operations people, they want me to run CentOS 3. I don't want to run CentOS 3. So they're smiling in this other one, right? But as soon as they have to talk to each other, it's like frowny faces. And the point that I want to make is our brains, we're awash in a sea of biases, and we can't really get around them. My favorite bias on here, by the way, is the IKEA effect. And the IKEA effect is the bias that we value things more that we built ourselves. That crappy bookshelf made out of particle board, but we spent our Saturday with those little diagrams that make no sense, and now we have a bookshelf. We're going to value that more than some nice mahogany bookshelf that is clearly worth more, but because we did that, we value that more. So here, I want to give you an example of how bias is built into our brains. It's an interesting one.
So what you'll hear is a sentence, a spoken sentence, that's been transformed by a computer to sound like gibberish. Any idea what they said?
No.
You can hear it one more time. Okay, now we'll hear the real sentence.
The Constitution Center is at the next stop.
Does it make sense that time?
Yeah, wait, was that the same?
It was the exact same sentence that you heard the first time.
No way.
It's the exact same sentence. Your brain is always using prior information to make sense of new information coming in. So once you know what the sentence is, when you go back and hear the distorted version, you can apply that information and it makes sense.
Isn't that weird? Now, the thing I want to ask you is, what do we do all day long in retros? We use all of our past data, and then we bring them into the retro. And the point I want to make with bias here is it's not like you can get around bias. It really is baked into the way that our brains function. And that previous slide of the hundreds of biases that there's papers on and researchers have studied them, the point that I am trying to make is we need to be aware of them. We need to be aware that they exist, and really high-functioning teams are good at being able to identify bias in each other and be like, okay, and recognize it, that it exists, but then work to sort of address it in whichever way, whatever the bias might be. Another resilience engineering anti-pattern that we see is deprioritizing retrospectives and learning processes. So has anyone ever had this problem where there's an incident on a Wednesday, and it's a pretty bad incident, so we solve it with a Band-Aid, and we say, we'll do the retro on Friday. Cool, all right. We get into the office on Friday, we're going to do the retro meeting, but that Band-Aid fails. And it's bigger now because we use the Band-Aid to fix it. It's a bigger incident. So it takes us all day, all 8 hours of our workday to fix the incident. And then we're like, okay, we're not doing a retro, we're going to the bar. And that's what we're going to do. So we say, we'll do the retro on Monday. So then we come in on Monday, and we find out, oh, wait, Sally, who was the main incident commander on this particular incident, she's on vacation. So we can't have, she's back, let's see, Thursday. So we'll do the retro on Thursday. Well, then on Thursday, we have an all-hands meeting. Okay, we'll do it next Monday. And soon, we're having a retrospective on an incident that is like 4 weeks in the past. People run into that problem all the time, or sometimes. So the point is that that conspires with bias, because what will happen is we'll take the data and we'll just fill in things using bias, and our brain is so good at this we don't even know it's happening. Now I have another question related to this deprioritization of learning and retrospectives. I want to go back to our thought experiment, and I want to ask you some questions. See if you know the answers to any of these questions. What's the aircraft's call sign? What type of approach was the plane on, an ILS or a visual? To what runway? Or was that runways? What heading did the controller order the plane to fly before the emergency? And what radio frequency does the controller hand the plane off to? Now, the interesting thing about this is this incident, quote unquote, happened 25 minutes ago. And I told you I was going to ask you questions about it. And I doubt anybody could answer with all of the questions here. And they're very matter-of-fact questions. And so here's my point. Our incidents don't tap us on the shoulder and say, hey, this is going to be a really good incident. You're going to want to pay attention to this one because it's going to be like a 36-hour thing. You're going to learn a lot. It's going to be a lot of fun. They don't do that, right? But when we go through these incidents and we don't capture that context, these are all factual questions. I didn't even get into how could you sense the stress in the pilot's voice? What clues did that give you about what was going on, even if you're not a pilot? And so in an incident, there's a bunch of really fine-grained heuristics that us as professional operators, we use all the time. But if we don't elicit that and think about it, very shortly after the incident, we can review logs all day long, but that's gone, and that's the thing that contributes to learning and our expertise. Okay, Act 3 of our 3 acts, resilience in incident remediation and prevention. And you'll notice that there's an asterisk near prevention, which we'll get into why that is. So this is the automate all the things, right? Out of curiosity, have people heard that meme? Raise your hands if you heard the automate all the things. Good, okay. Anyone's like, I don't want to automate all the things. I'm tired of hearing that. I feel like that sometimes too. So there was a paper done quite a while ago. The date on this is 1983. Researcher thinking about what are the ironies of automation? If we have a world where lots of things are automated, what are some downsides? What are some weird kind of strange things about automation? And so she brought up, the quote here is, the paper suggests that the increased interest in human factors among engineers reflects the irony that the more advanced the control system is, so the more crucial may be the contribution of the human operator. So she came up with a bunch of ironies. We're going to look at my favorites. The first one is probably pretty obvious. Manual skills deteriorate when they're not used. So if we have a process that we use and then we buy a tool or we write a tool to automate that, if that tool breaks for some reason and we haven't had to do that task for a month or 6 months or whatever, our skills are going to deteriorate if we don't use them. The generation of new and novel strategies requires an adequate knowledge of the system. And the point here is new and novel strategies refers to in an incident when things are broken and you need to do something to work around things that are broken. That's a new and novel strategy. If we lose knowledge of the system because it gets encoded in some automation tool, then that inhibits our ability to come up with those new strategies. Automation generally requires a speed versus correctness trade-off. So I have a lot of interesting discussions about this. But at its heart, why do we automate things? Well, we automate things for a lot of reasons. But one of them is computers are really fast at doing things. The problem is if we use computers to automate other computers, then those computers are going to do that work too quickly for us to validate it. So we can never validate correctness of automation. We can't, because it moves too quickly. We can validate that it is acceptable. It more or less does more or less what we wanted to do. But in terms of being able to prove, if you like the standard, maybe prove in a court of law that your automation did the right thing across a fleet of 1,000 instances, you can't do that. That's kind of the point of automation. It moves too quickly for us to check it. And finally, automation can camouflage current system state. So most of the automation and control systems that we use, and you see this a lot in auto-scaling, Kubernetes, and things like that, automation is designed to work to certain boundaries. And those boundaries are usually specified by engineers when they build that automation. But the problem that we see in a lot of control automation, and this is things like boats and planes, when the automation is getting near the limit of what it is able to do, see this in autopilot, right? The yoke is cranked to one side because the autopilot is trying to turn the plane one way and it's not turning. When the automation gets to that limit and then maybe fail-safes or turns off, then that yoke is going to come all the way back if there's a force fighting it for some reason. So the point is that automation can leave us in a state when it reaches its limits, can leave us in a state that is much worse than we would have allowed the system to get into if we had been doing it by hand, because we would have made corrections further up the line. But automation doesn't know that. It's like, I know what I can do, and I'll go to the boundary of what I can do, and then when I get there, I'll be like, eh. Tracing the decision tree made by algorithms can be difficult or today impossible. This is a direct nod to AI and ML, right? If you roll up on an incident and you've got some automation that's doing stuff, or you've got automation that's purchased, you've purchased it from a SaaS provider or something, so it's a black box. The automation that you're using is a service. It is hard for us, and in this case difficult or impossible, to actually look at the decision tree that automation made to get us to where we are. Which, if you look at the way that we remediate incidents when we're in the moment, when we're looking at what changed primarily. And if we've got a system that left us in a spot where we don't know how it decided to get us there, that's harder for us. And this leads to the inability to fully understand the current context of the system when you get paged. You show up, and you probably have had this experience. You show up and you're like, none of this makes sense. Like, what? The auto-scaling groups did what? Why? That is an irony of automation, one of the harder ones. I want to talk a little bit about joint cognitive systems because it's important. So what do I mean by joint cognitive systems? Well, in a system, we've got operators. Operators have autonomy. That means that they can work by themselves. They can do things by themselves. They have authority. That means that they can actually push buttons. So autonomy is I can act on my own, and authority is I can actually affect other things. Directed attention. So that means humans have attention. So I can look at you and I can say I am talking to you. This is where my attention is directed. There's also the idea of redirectability. So if Mike up here is like, hey, pay attention to me, I can, oh, okay, I can pay, you can redirect my attention. And then interpredictability. So we see this on teams all the time. We have team members, we can sort of interpredict generally what they're going to do in an incident. We might have defined roles to help us with that interprediction. But teams that are high-performing or have worked together for a long time have a strong sense of interpredictability. So let's look at automation. Well, automation is certainly autonomous, right? That's the point of it. It can do stuff on its own. We give it authority. We give it access credentials to do things to our Amazon accounts and our machines and other things, so it's able to act. Does it have a directed attention? Can you ask your shell script, what are you currently paying attention to? Can you ask your shell script or your Kubernetes engine, hey, stop doing that because I need you to pay attention to this? No, can't do that. And we've all run into situations. If you've ever said to any automation anywhere, what are you doing? Please stop. That's a loss of interpredictability. So here's the point, though. These are the foundations of coordination. These are the things that humans do when they're working together, and automation can't participate in that. There's a great quote, technologists often mistake connectivity, the ability to observe things and maybe affect them, for coordination. And I said that you would see the Sharky picture. These entities are connected. I don't think they're coordinating. So I want to talk a little bit about the AnimaC Paradox. This is the last part of this act that we'll talk about. So automated systems, as they increase in autonomy authority, have two kinds of interpretation. So in other words, as they're able to do more things, there's two ways for us to think about them. One of them is as a deterministic machine. And so automation has a list of steps. We've programmed it. We know what it's going to do. So we could draw the state machine on the whiteboard if we wanted to. It's deterministic, right? We can also think of it as animate agents capable of activities independent of the operator. And we've all experienced this when automation is running around doing things and we're like, why is it doing that? Now, what is the difference between these two interpretations? One of them is in foresight or hindsight, and that's when we're designing automation, we generally design it with boundaries and limitations and a flow chart and if this, then do that type logic. So we think it's deterministic. Also, though, in hindsight, after we have an incident that was caused by automation, we'll go look at the code and we can, oh, there's a bug there, or we didn't expect that thing. So we can figure, it's still deterministic. It's totally deterministic. We just didn't design for that. But we still think of it as deterministic. But in context, in the moment of an incident, that's where we see this. I don't know what it's doing. I wish it would stop doing that, right? And that is the point here is what's the difference between these two? It's when you are in the midst of an incident. When you most want to have the ability to think of it as a deterministic machine. That's when automation is running around doing stuff that we may not fully understand and which is costing us potentially millions of dollars. So the reason I brought up the Rasmussen triangle is because there's a very critical point about automation that I want to make. And that point is, again, remember, teams that are really good that we look up to at their operations skills are good at exploring the discretionary space. But guess what? Automation can't explore that space. It's incapable of doing that. And it can't do that with us. That would be coordination, which, as we've seen, it can't do. So how do you deal with some of these ironies? So this is just a few thoughts if you're designing automation or using automation to think about. You want to engage in practices that cultivate the ability to buy time. So what we mean by that is buy time in the context of the automation is going wrong. So if you want the autopilot of an aircraft, you want to design that automation such that if a mistake is made, the pilots have the opportunity to figure it out and correct. And by the way, if you want the best counterexample right now, the 737 MAX is an example of automation where they didn't design it to allow the pilots to have that time. How do we do that? This is why chaos engineering comes up again. This is why game days and tabletops come up again. Simulation helps us buy time. It helps us get better at the skill of buying time. Widen system understanding as daily practice. So the point is, this is why, as stupid as it sounds, things like brown bags, learnings, lunch and learns, things like that. Because we tend to often, especially in systems that are more automated, we tend to just kind of let them go. And we may not spread that knowledge about the internal workings of the system very far. So that's important, and the reason it's important is because it contributes to this. Co-evolve automation with a product it supports. I don't see a lot of people treating automation, their own custom automation that they write or that they plug into, as a product, with a product owner and a roadmap that is somehow related to the service it supports. Co-evolution can help with this. And then also consider the element of operator time pressures in the design of automation. And this goes back to the whole buying time thing. All right, so epilogue. Now that we're done with our 3 acts, these are some of the takeaways I hope you have from today. So in the context of resilient engineering and incident response, expertise takes time and space. So if you want your teams to have expertise, you need to make that time and create that space for them to become experts. If you don't do that, then you're going to inhibit their ability to cultivate expertise. In incident analysis, so beware of our brain's biases. There's a ton of them. But here's, if you take anything away actually from this talk, the one point I would really want to make, success and failure are 2 sides of the same coin. What do I mean by that? The things we do every day that make us successful are also the same exact mechanism that contribute to failure. And that's really, it's one of those things where you kind of, it's, the first time you say calculus or something, like, wait, what, huh? But it's true. And that's why asking questions about what things are working well, why is the site up, is so important. This bit, the joke I made about you have 72 hours to learn, hopefully I've proven to you that, yeah, if you are not doing a retro within about 72 hours, you're not going to get the learning benefit. You're going to have a bunch of people in a room with a bunch of logs and you're going to put together a timeline, and then your brain will very dutifully reconstruct the context for you, and it will not be the context that existed. And that is probably fine, but you're not going to learn as much as you could learn as if you had had that closer to the event. And this statement comes from, like, firefighters actually do mini retros at the end of most fires. Interestingly enough, they do it. There's a name for it which I'm blanking on, but they actually do it at the back of the fire truck. They just get around and go around, and they talk about that particular fire for this reason. Incident remediation and prevention. I didn't explain the asterisk. You can't prevent incidents. A lot of people think, oh, with automation, let's automate that. We'll prevent the incident next time. If you've ever had that, I always chuckle when I hear that because I've had plenty of that in my career. Oh, we'll automate that, and then the automation causes the incident. And you're like, no. So automation that truly participates in our joint cognitive systems. These are the systems that you and I work in with our team members and our technology, socio-technical systems, is very nascent. It's not as evolved as we would like to think. And by the way, aviation and hospitals have automation that is way far ahead in the way they think about this problem than the way we think about it. And part of that is because there are directly attributable lives at stake. But we're not as advanced as we might think. And then finally, caveat implementor. When you implement automation, it's a responsibility, and you should take it as such, because there are a lot of ways it can go wrong. So and basically what I mean is when someone says, I'll just write a shell script for that, which, by the way, I've been guilty of saying in my career. So it's like, we might want to talk about that shell script before you write it. That's all I got. Thank you.